So we're still waiting for your colleagues. Can you see my other screen now? I shared the PowerPoint.
No, we can't see it.
No?
No.
طيب. Let me. Okay. Let me just. Okay, now you can see it?
Yes.
Okay.
Yes.
So if you have no questions, then we're gonna finish a small part in the wing design that we had last time, and we're gonna move on to the remaining of the configuration layout. Last time we designed the wing in a sense that we started with the wing area, we selected proper values for the sweep and for the taper ratio, aspect ratio calculated until we found the dimensions of the wing so that we were able to draw the wing. We have all the dimensions, we calculated the mean aerodynamic chord, and the only remaining part was where to place the wing. Should we have it a high wing? Should have a low wing? Or should we have the wing in? Each one of them is good in one thing, which is the one in green here, and bad in the other, which is the one in red. So a high wing is good for stability, but sometimes it's too much of a stability. So that makes the aircraft difficult to maneuver. So that's why you see most transport aircraft have a high wing for increased stability. Mid-wing is reasonable in terms of stability. There is no interference between the wing and the fuselage. The only problem with the middle wing is that the wing has to be cut in half. That means I have to connect this half in here, this wing half in here, and that would require a strong, very strong structure. Or if you want to have one piece, the wing as one piece, you will have problem inside the fuselage. You will not be able to use the full volume of the fuselage. Now for low wing, I can have a continuous wing, so I don't have any structural issue. But for stability, I must have a dihedral. That means the wing has to be up in order to stabilize the aircraft. And in doing so, I will have a pocket of air here that will create interference between the fuselage aerodynamics and the wing aerodynamics. So each one of them has some issues. Other considerations that the team should which type of wing is, what about the landing gear? Are you going to have a low, if you have a low wing, I can retract the landing gear right away in the wing and it will be a short landing gear. But if I have a high wing, I cannot retract the landing gear in the wing. It will be a very long landing gear, and that's an issue. So the landing gear is another factor. Also, do you have something hanging from the wing? A missile, a bomb or so? In this case, you have to be careful with low wings. Maybe I can go medium, or an engine maybe. So that might be an issue. If you have an engine, I will not have enough room here for the engine. So maybe a high wing will be better for this. A high wing is also good for the engines because if you are going to operate the aircraft from airfield in the desert, for example, if you have a high wing with an engine, you have less chances of this engine sucking dusts from the ground or debris from the runway. So that's another factor. So all these are factors to be considered in your aircraft. So for transport aircraft, typically you will see the wing is low wing because I need to put people on the top. If I have a middle wing, I will not have room for the seats. So typically it will go with a low wing or medium to low, so that when you attach the wing, it looks like this. So it must have a dihedral, it will go up. So you will have some interference between the fuselage and the wing. And by going up, you will have room now for the engine and you will have good stability. You are having the wing continuous now because it will go under the fuselage. So I can have a continuous wing. So there is no structural issues here, and on which the fuselage can come and they will be connected together. Or if the wing is very big, I have a center section of the wing going inside the fuselage, and to the other parts of the wing will be attached, but it's structurally, it's still one wing. Okay. This is good for low wing, and it's the same case for high wing. So for the transport aircraft that's produced jointly between the kingdom here and Ukraine, you have a high wing configuration where you have the structural wing continuous, no issues. You have room for the engine, and the long landing gear now that was very long. If I connected to the fuselage, now I connect it to the engine pod and it retracts in the engine pod because it's not that long anymore. Okay, so based on this, the team should look at the different factors that I talked about: aerodynamics, landing gears, ground clearance, do I have room? And then you choose what type of landing gear you want. So for the aircraft that we have, it was decided to have a low wing because it's a passenger aircraft. And we know all the good things and the bad things about the low wing. Okay. So this part finalized is the wing design that we have, where you want to place the wing, low, medium, or high. Any questions? Okay. So
I have a question.
yes.
I didn't understand how is the wing related to the landing gear.
Oh, okay. You see this aircraft here. Assume
Yes.
that I don't have the engines here, or maybe the engines were attached to the fuselage or inside. And in this case, the main landing gear, if you want to attach it to the wing, it's going to be very long, right?
Yes.
The landing gear will go from here all the way to the wing. In this case, you will not be able to retract it inside the wing. You will not be able to retract it inside the fuselage, because in this case, you will have that column hanging in there coming like this. So in this case, if you design a high wing and you don't have an engine here to retract the landing gear, we maybe have a pod on the side where we retract the landing gear directly into the fuselage, just like the C-130. So the C-130 would have a pod in here in which you retract the landing gear. Now, so in this case, the wing has nothing to do with the landing gear. It's attracted to the fuselage. But in many aircrafts, you see this one, the landing gear would retract directly into the wing, because the landing gear here is small, it's thin, and I can put it in the wing. That will save me considerable room inside the fuselage that I might need later on. So that's how the wing and the landing gear is related. You see this wing, I am able to retract the landing gear in because it's short and small. I wouldn't be able to do this if this wing was a high wing. Does this answer your question?
Yes, thank you.
Okay. Any other questions? So you see, most of the stuff on this section, which is the configuration layout, is not equations, it's not tables, it's just common sense. Reasonable discussion, justification with your team, why and why and why, and you come up with something that you can justify and use. There is no equation that will tell you put this a low wing or a high wing. It's the use of the aircraft. What are you going to use this aircraft for? Okay. Okay. Let me open the other one. Did the slide change? Can you see the new one, or do I have to
no.
select? No.
Yeah, we can't see anything now.
You can. How come?
No, we can't.
I didn't hear that. Can or cannot?
Cannot.
Cannot.
Oh, you cannot. So, okay, let me. There must be a way to do. Okay, let me share the whole thing in here. Okay. Now?
Yes, we can.
Okay. So we are still in step number 4, configuration layout. We are done with the wing. Today we are going to look at the fuselage. And you realize we are going to go one component, one by one, from one part to the other, from the fuselage body to the tail to the propeller to the landing gear. And in doing so, we'll gain more information of the aircraft. Let me remind you what exactly is configuration layout. It's converting the numbers that we had before that satisfy the requirements, converting these numbers into dimensions. I want to draw the aircraft. Right now, the only part that you can draw is the wing. Okay, so we would like to draw the fuel tank, for example. So let's see how we're going to draw the fuel tank. Do we have the weight of the fuel? Yes, we do. In the WF that you had, hopefully in the progress report that you will submit today, you have calculated the weight of the fuel. And when you divide by the density of the fuel, I will get the volume of the fuel tank. We had that before, 145 gallons. But I need to convert that number into dimensions. How many inches, how big the fuel tank. So before we do this, let me summarize where do we put the fuel tank. For those who do not know, for those who taking AE240 as the first aerospace course. In the wing, we have a strong beam that will go from the tip to the root. That's called the spar. And typically we have more than one beam. So we have this as the front spar and this one strong beam as the rear spar. In a top view, that will be the front spar and that will be the rear spar. Typically, the front spar is located at 1/4 of the chords. So you see this line, typically, not always, but close to 1/4 of the chord. Typically, the rear spar will go around 70% of the chord. Typically also, it could be 65, it could be 75, not a big deal. The exact location of the spars is determined by structure analysis that you will study in AE 328. And that's beyond the scope of this course. But here we can assume reasonable front spar and reasonable location for the rear spar. Okay, remember I have the wing, so I can decide I will put the front spar here and I will put the rear spar here, and the spacing between them roughly would be half the chord at the root, which would be 3.27. Now, what if it's 3.3? No big deal. 3.5, not a big deal. Okay, so I can have that chord in here. Now, between the front spar and the rear spar is where we put the fuel tank. Okay, we put it in the strongest part of the aircraft between the front spar and the rear spar so that it's protected. The question is how big the fuel tank is going to be. Now, the fuel tank is constrained by the volume that I have in here. The only way to have a bigger fuel tank is to make it longer. I cannot make it thicker because I'm constrained by the airfoil. I cannot make it wider because I am constrained by the front and rear spar. So the only design parameter that you have is the length of the fuel tank, how long the fuel tank is going to be. So in order to draw the fuel tank, I know the distance between the front spar and rear spar. here. I know that the distance will be that much here. It will decrease until it becomes the distance between 1/4 and maybe 60 or 70% of the chord. So I know it will reduce down. I know that the height is constrained by the airfoil. If you were with us from the beginning, I showed you one way to get airfoil information, one library. Probably you all know that you can get the coordinates of the airfoil, so you know what's the height inside the airfoil. So if you draw the airfoil for this example that we had, at the root, for example, in here, you will realize that the biggest tank I can put inside would be around 0.9 feet. Here we take 0.8 just to make sure that this chord will go smaller and the thickness will become smaller. So we make the height of the fuel tank as 0.8. No equation to tell you the 0.8. Please don't send me this on WhatsApp. How did we get the 0.8? It's just common sense. You draw the airfoil just like you play with Lego or Meccano. What's the biggest tank that will fit inside that fuel tank? And maybe you want not to take the biggest, but a little bit smaller, just make some room, extra room. So 0.8 feet, for example. The question now is, what would be the length of the fuel tank? If this distance is fixed by the front and rear spar, this distance will change depending on that length, because the more length, the less distance, and the thickness is fixed by the airfoil. So what I can do is we can calculate, there are several ways. The easiest brute force way is to assume a length, calculate the area of this trapezoid, the average base times the height, multiply by 0.8. If it gives you the volume that you need, then that's your fuel tank. If not, then make it a little bigger. Try it until you get it. Or you can relate this distance to that distance if you want. Okay. Now, how big the fuel tank is it was 145 gallons, converting it to cubic feet, and that's the conversion factor. Gives me 19 cubic feet. Since I have 2 halves of the wing, I will have 1 tank here and 1 tank here. So half of this is 9.7. So I need the length that will give me a volume of 9.7 cubic feet. Now let's calculate that to check that this length will actually give me the 9.7. 3.2 plus 9.9, 2.9 divided by 2 is the average base. Multiplied by this will give me the area. Multiplied by the 0.8 will give me the volume, and that will be the 9.7. If you need more room, you will have to take more length and you will calculate the new volume. If you want to relate this dimension to that dimension, actually you can do this, and I am going to leave it as an exercise for you. You can get this distance as a function of that distance from geometry, simply from geometry. Okay, but you can try it. You can try several values. If the fuel tank is very long, let's say the fuel tank will go to here, that would not be acceptable, because that will mean the wing is going to be very heavy. It might break. It's not designed to carry that much fuel. Typically, fuel is inside the inside 1/3 of the wing. So if that's the case, then we might think of having a 3rd fuel tank, maybe in the fuselage, depending on the type of the aircraft. So I'm going to stop to see if you have a question for the sizing of the fuel tank. We have just decided to get the dimensions of the fuel tank. So when you draw your fuel tank in your final report, don't draw a black box like this and write inside the volume is 9.7. Well, I know that from the numbers that you have. You have to give me the dimensions. And when I multiply the dimensions, I get the 9.7. Okay, so please don't write the constraints, just write the dimensions. Try the dimensions that will give you 9.7. Okay.
Victor?
Yes.
Do we have 2 fuel tanks?
Yes, we can have even 4 and 5. In this case, we have actually 2, one on this half and one on the second half. In transport aircraft, actually, we are going to have 3 or 5, I would say. 2 in each half wing and 1 in the center section. But for your aircraft, which is a small aircraft, very short range, And from what I saw last night, you guys have very little fuel consumption. One fuel tank in the center section or two in the wings will be more than enough. You will not need more than that.
Okay, what
Other
about
question?
the consumption of fuel? I mean, how do we know how much fuel we need?
No, that's not an assumption. You calculated it.
Yes,
Remember?
I mean, how do you calculate it? Is it from the weight estimation?
Yes, WF. The weight of the fuel is WF that you have calculated in the weight estimation. And when I divide it by the density of fuel, I will get the volume of fuel. And we did that. We have the volume of the fuel tank. Okay. The only thing that we do in this slide is we are taking that volume and we are converting it into 3 dimensions of the fuel tank. That's the only thing we are doing. Okay. Any other question? Okay, I have to go and check. Okay. The second part that we will move on is the fuselage. We want to convert the constraints that we have in the problem, the number of passengers, the engine, the baggage, into give me dimensions of the fuselage. How long it's going to be, how high it's going to be, what would be that height, what would be the width of the fuselage. This is the question that we want to answer. Again, just common sense. Think of it like, again, playing with a Meccano. I want to fit 6 people inside in here. So probably you are going to put them 2, 2, 2. Most probably it's not going to be 3 and 3. Just like a car, just like the seating arrangement of an SUV car. So what would be the height of the seat? You can turn around and see the height of the seat you are sitting on right now, because the one in the aircraft will be close to that. Okay, about 90 centimeters, a little bit less than that, maybe 80 centimeters. What would be the height? So the dimension that we have here is for a typical person sitting on a seat. So that will give me the total height that I have in here. Okay, maybe a total height of the aircraft would be, what would the number that's chosen in here, about 4.5 feet, about one. How high would that be? 140 centimeters. It will be less roomy than a car for sure, because volume is an issue. So we can have a height of 4.5 feet. Okay, that's for a person sitting. Now, what would be the distance between the seats? Again, think of the distance between your seat and the next seat when you were sitting in an aircraft. What's the comfortable distance? Of course, first class will have more room, economic class will have less room, a general aviation aircraft will have even smaller room. So typically around 3 feet from one point to the other point. Not 3 feet in front of you to spread your legs, it's 3 feet from the back of your seat to the back of the next seat. That's all the room that you have, about 90 centimeters. Okay, now this distance is different from in transport aircraft. It's different in first class, and there are several. You can search these on the net. Textbook of 427, we have that. There are so many ways to find these numbers. The typical width of a seat is about 1.67 foot. That's about half a meter. 50 centimeters is typical for the width of the seat. Okay, not very wide, you can guess. So knowing the dimensions, I can determine that the length of the passenger cabin will be 333, that's 9 feet. The height maybe 4.5, and the width will be more than 2 seats. The 2 seats is 3.34, so I might get a little bit more. So let's take 4.5 feet. So it was chosen as 4.5. What you see here is the section at B and the section at E. So what would be the length and the width? You see the width is 4.5 all over the aircraft. The height here is 4.5 feet, about 130 centimeters. And the height here is determined by the height of the engine. So I have to ask myself how big the engine is. Remember, we have selected the engine last time or the time before. We have selected the type of the engine. So a small visit to the website of the manufacturer will tell you the dimensions of the engine. And we did that, by the way. These three numbers, we had them before. The length, the width, the height. So I need to put the engine here, so that will determine the width and the height of this section AA. Of course, you make it a little bit bigger, both in the width and height, so that you will have room for the other components, which we will not design, of course, in here in AE240 conceptual design. You will do this in AE427. So we'll have to make room for the hydraulics, for the avionics. You will have to worry about everything: air conditioning, entertainment systems, batteries, and so on. But here we are talking about the main components. Finally, before I see if you have questions, the last thing that will need room inside the fuselage is the baggage. Remember, we had like 120 pounds baggage. So if I can convert this into volume, how big would you put 120 baggage? Again, that's common sense. 120 pounds, about 60 kilograms. You can say I have 3 large pieces of luggage or 4 medium pieces. So how big these are going to be? Will they fit in the tail cone of the aircraft? And I can draw the tail cone of the aircraft. If I have a height of 4.5, maybe I can have that length, maybe about 10 feet, so they can have a slope tail that will reduce the pressure drag. And in doing so, I have found the dimensions of the aircraft. Now, the dimensions that you see in here, this length in here, this height, this width, you see, not a single equation, just common sense and typical values for the industry that we can use. So, any questions in the sizing of the fuselage? Unlike the wing, we don't have equations here. The fuselage is determined by what you want to put inside: an engine, seats, baggage, and maybe some room for the wing and landing gear, if the landing gear is going to be retracted inside the fuselage. Okay. Any questions? Now, to move on to the remaining components, basically what's missing now is the propeller, the landing gear. These are the two items: propeller, landing gear, and the tail. But the landing gear and the tail depend on where you want to put the wing, and they depend on where is the CG of the aircraft. But the CG of the aircraft depends on where is the landing gear and where is the tail, because there are two components that we have to. So you see, we have a problem here. We have a dilemma. It's like chicken comes first or the egg. I need the tail location and size. I need the landing gear location and size in order to get a good CG. But I should know where is the CG in order to get the area of the tail. So that's a problem. So in order to solve this problem, what engineers would do is that we calculate the location of the CG without the tail and the landing gear, with everything. And then when we calculate their location and sizes, we refine the location of the CG. That's why in the steps, we have here what's called a better weight estimate. So the better weight estimate, meaning we will include the location of the tail, the landing gear, and maybe other smaller components that we can include. Let's say the weight of the seats by themselves, the weight of the landing gear, hydraulics, whatever additional components. So for now, we will calculate the location of the CG without regard of the tail and the landing gear. Because once we calculate that CG location, I will be able to design the tail and the landing gear, and then I will include them in a new CG calculation, and then I will check their areas and so on. That's why it's a cycle. So let's determine the location of the CG. What are the main components, the heavy components that I have? I have the engine. I know its location. and I know its weight. I have the people, I know their weights, and I know the location, which is obviously the center of the passenger cabin. I know the baggage, 120, and I know where I want to place it, and I can put approximate location. So please stop asking, how do we get these dimensions? Again, common sense and reasonable measurements from this dimension. It's not an equation that will give you the 19.7. This number will be refined when you draw the aircraft on SolidWorks and find, okay, maybe it's not 19.6, it should be 19.2. So I will go back to my Excel sheets or my notebook or my MATLAB code, and I will refine the number, and the location of the CG will be refined. So if I do so, can you find the location of the centroid? Yes, you did this in math or mechanics in high school. You multiply each force by the arm, each force by the arm, each force by the arm, and you add the 3 moments, and you divide by the resultant force. That will give me the location of the resultant, which is the centroid here, right? Summation XA divided by summation A, that will give me the location of the CG. So the CG is 7.72 feet from the nose of the aircraft. Typically, we measure everything from the nose. Is this clear? So that's the CG. Well, I can maybe put the wing as well. Not only these 3. Well, I have the area of the wing, but I don't have the weight of the wing. So again, designers would rely on experience, previous data, historical data, searches in order to find what is the weight of a wing that is that big. So there are several resources on this. Okay, a company would rely on its own experience. For us here, students looking for numbers, maybe a textbook. So in the textbook of A427, it relates the area of the wing directly to its weight. It says if you are designing this wing for a general aviation aircraft, a good estimate of the weight is to multiply the area by 2.5. So if the area is 176, multiply by 2.5, it's 440. How did they get the 2.5? They related the areas and the weights of so many aircraft and got an average. Can you do this for your aircrafts that you have? Unfortunately, the data you collected from the internet probably will not have the weight of the wing, probably. So you can look what's the factor for aerobatic aircraft. This factor is 2.5 for general aviation aircraft. It's about 9 or 10 for fighter aircraft. So I would say aerobatic aircraft will be somewhere in between, because they are expected to have high G loading. So maybe not 2.5, maybe 4 or 5. Okay, maybe 4 or 5. And we are going to try the value and see if it makes sense. In 4 to 7, you will get a little bit more accurate way to estimate that. Okay. Now, why it's difficult? Why cannot we get it from SolidWorks? Because if you draw the wing in SolidWorks, it will give you the weight of the solid wing. But as you see here, the wing is not solid. It depends on how many stringers, booms, thickness, and so on. We don't have that yet. So if I add the weight of the wing, and the CG of the wing is typically taken at 40% of the mean aerodynamic chord. This is the MAC, the mean aerodynamic chord. 40% of that is the CG of the wing, not 50, because the wings are heavier and stronger towards the leading edge. You see this one? They are heavier, they are higher than the trailing edge here is thin. So the CG is not exactly in the middle, it's about 40% of the chord. So 40% of the chord plus this distance because of the taper, plus where you want to place the wing. So if we decide we want to have a CG of the wing of about the location of the leading edge of the wing is about 7.72, so that's the arm of the wing times the weight of the wing plus the moment that we had for the other 3 components gives me the new CG with the wing, 7.87. Now this might be a little bit confusing for you. What you can do is not to have this drawing, not with 3 parts, but with 4. Draw the wing here and you're going to have a force force. 1, 2, 3, 4. Each one of them, you have a weight and you have an arm. Here is the weight of the wing and here is the arm. And that will give you the total CG location, including the wing. I hope you will be able to do this for your aircraft because you have all components as well. Yes. Question? Any question? No, you should have questions here. Unless you are in the background doing the progress report to be submitted. I think that's a good location for questions. Okay, I had a good question from section 2. They said that's fine, that's the location of the CG, which is important for stability, of course. But what if I don't have everyone here on board? What if I have only the pilot flying the aircraft? Wouldn't this affect the location of the CG? And the answer is yes. What if I have only 2 passengers? Would that change? Yes. What if I have 3? What if I don't have luggage? What if I have full? What if I have fuel? What if I don't have fuel? All this will change the location of the CG. But the location of the CG is important for stability. So what designers do is that we calculate all these values of CG. So it's not like a single value. We have so many of them, 10, 20, depending on the different possible configurations, with, without fuel, with, without passengers, with, without luggage, pilot only, and so on. And after I look at all these values, we determine what is the shortest one, what is the forwardmost one, and what is the longest one. That means what's the aft. That means the CG will change between this point and this point. No matter what we do, how you load the aircraft, the CG will be between this value here and this value here. If the aircraft is stable at these 2 values, it's stable everywhere else in the middle. Does that make sense? So we calculate what's called the travel of the CG. The CG will travel between this point. Maybe the CG is here. It will go sometimes like this, or it will go like this, or like that, or like that. But it will be confined between 2 limits. We just check the stability between the 2 limits. But here for us in AE240, first time we're doing this, we will check stability only when the aircraft is fully loaded. Okay. By the way, in earlier designs in the 1970s and 60s, particularly Russian and Chinese aircraft, they had problems stabilizing the aircraft at one of these limits when the aircraft was empty, not when it's loaded, but when it was empty. There was a problem in stabilizing the aircraft. So what did they do? They could have changed their design, but the design was good for other purposes. So they used sandbags, which was not a very efficient way. So the aircraft cannot fly empty. You must have sandbags in certain locations to stabilize the aircraft. Not a very good solution. You could have a better design, but it's a cheap solution if you want to keep the same configuration for other purposes. Any question? Okay. The last item that we will look at today is the tail. Now that we have decided on where is the CG is at 7.87 feet from the nose. How big and how far the tail is going to be. The tail main purpose is to generate moment about the CG. And I understand some of you have not taken any AE course before. So for this, please bear with me here as we explain how does the tail work. The moment of the tail is proportional to the area of the tail. The bigger the tail, the more. The longer the distance between the tail and the CG, the more the moment is going to be. So you have two design parameters at designer. You need to determine how big the tail is and how far aft of the CG you are putting the tail. Now, how much moment should it provide is determined by the moment generated by the wing. The moment generated by the wing is proportional to the area of the wing and the chords of the wing. Now, the ratio between these two moments is called the tail volume ratio, and it will represent how stable the aircraft is. The higher the tail volume ratio, the more stable the aircraft is. So transport aircraft will have a high value of this, 0.8, 0.9, and so on, close to 1. A military aircraft will have a low volume ratio because you don't want the military aircraft to be too stable. You want to be responsive to control inputs. So maybe 0.3, 0.4, okay? 0.5. So for your aerobatic aircraft, maybe a 0.5. Do some search on what's the tail volume ratio for an aerobatic aircraft. So we have this tail volume ratio for a horizontal tail, and we have the same thing for the vertical tail. Okay. Now, why are volume ratios important? Because they don't change much between different aircraft of the same category. They are a good starting point. A volume ratio is for the horizontal tail is the area of the horizontal tail times its arm above the CG, area of the wing times the chord. For the vertical tail, it's the same thing, except that it's the span that matters. It's the arm for the moment of the wing. Now, if we know the volume ratio, if I know this number 0.7, this number 0.04, if I know everything in the denominator because it's the wing, I know everything about the wing, the only unknowns are what we have in here. Area of the tail and arm, area of the tail and arm. So you have to choose the type of the tail, and there are several considerations to choose the type of the tail that you'll probably learn as we go. Right now, you can pick anyone. Sometimes the considerations are design considerations, stylish. For example, a T-tail would look stylish. I mean, it's like different. It's just like you have a spoiler in the trunk of your car, right? So sometimes you see it in business jets because it makes the aircraft sales. It's different. That's one fact. The other factor is it's good because it's away from the wing, or maybe it will give room to put the engine. There are several factors. But for us here, let's say we'll choose the conventional tail. If I do so, then the question would be, what is the area of the tail and how far the tail from the CG? Well, I can get how far the tail from the CG because I know the CG and I know maybe the tail will be towards the very back. So I can choose that number reasonably. And as such, the only unknown will be the area of the tail. So I will get the area of the tail. The same for the horizontal, for the vertical tail. I know the vertical tail is going to be here, so maybe that distance is going to be 16 to the center of it, 16. So I will get the area of the vertical tail. Reasonable areas that I will change later on when we do another cycle of the design. Okay. Is this configuration? No, these are just areas. They are not going to help me. They will not help me to draw the tail now. I must convert these areas into dimensions. Okay. So if I have these areas, I can get the dimensions in exactly the same way I got the dimensions of the wing. Remember the wing? I had an area, some taper ratio, some aspect ratio, and I was able to draw the wing. From a geometrical point of view, the horizontal and the vertical tails are just small wings. If you ask your young brother, what is this here? If he doesn't know it's a tail, he'll tell you it's a small wing, right? Just like a wing. So from geometrical point of view, I can take the area of the horizontal tail and I will use the same equations that we had for the wing. The span, the aspect ratio, the chord root, the tip root, even the mean aerodynamic, and I will calculate this for the horizontal tail and I will calculate this for the vertical tail. And thus I have converted the areas into dimensions. Exactly the same thing. The span is exactly the same equations that you did in the wing if you have included the wing in your progress report. The span is root square area times aspect ratio, except that it's not the area of the wing, it's the area of the tail times the aspect ratio of the tail. What about the aspect ratio of the tail? Remember, the wing was about 6 or 7. We know the tail is going to be shorter, so I can assume 4. We can put it 5. And there are some tables, some resources to assume these reasonably. Okay. Similar aircraft. You can look what's the aspect ratio of the tail of a similar aircraft in your category, and you can use that initially for this. And then we have equations. We use the same equations in the wing. These are not new equations, but I will use the values for the tail. And when I do so, this will give me the tip chord, the root chord, the span of the vertical tail, and the same of the horizontal tail. And as such, I was able to draw the tail thing in the aircraft. The only components that I don't have now drawn is the propeller and the landing gear. And we are gonna wait on these for next time. So next time we will determine how big the propeller is and how long the landing gear is. And what are the tire diameters? Are they having R13, 14, 15? What's going to be the diameter of the landing gear? Okay. So you see, it's more of a discussion and decision making rather than exact calculation. You see this 16, you could have had it 15.5, and it's not going to make any difference at this level. Later on in your study, you still have a couple of years to study, you will see that actually maybe we cannot move it forward a little bit. There are other considerations. For example, you will learn there should be some interaction between the vertical tail and the horizontal tail. You want the rudder to be effective even when the horizontal tail stalls. Other considerations, but they are beyond the scope of this course. Any questions? We have a couple of minutes if you have any question. Okay, so I think